For our third example with Coulomb's law, we'll again look at three charges, but instead of having them all in a line, they're going to be in a plane. So we'll have to use vectors to figure out the magnitude of force in this particular problem. So let's go ahead and set up our picture. Y-axis and x-axis. Let's go ahead and make some marks here just to denote my scale. And we'll go ahead and say the unit here is meters for simplicity. So that means this is 1 meter, 2 meter, 3, 4, 5, 1, 2, 3, 4, 5, 6. Alright, so I've got charge 1 is going to be right here. Charge 2 I'll place down here. And then charge 3 is going to be over here. So if I wanted to write the locations of each of these, for charge 1, the location is 0 in the x direction, 2 in the y. For charge 2, it is 3 in the x direction, 0 in the y. And charge 3, 5 in the x direction, and 3 in the y. Just in case you're having trouble reading that. Now, next up we need to know what these charges are. Charge 1 is equal to 2 microcoulomb. Charge 2 is equal to 1 microcoulomb. And charge 3 is equal to negative 5 microcoulomb. So we're going to look at opposite charges in this particular example. Now, the next thing we need in order to go through and examine this using Coulomb's law is the distance between each of the individual charges. Now, we know what their positions are, so we should be able to use that to easily figure out the distance between them. So, just as a reminder, r is equal to the square root of x squared plus y squared. So, if we want to know the distance between charges 1 and 2, then that is going to be the difference between their x position squared plus the difference between their y position squared. So, for these two objects, this is going to be 9, because the x position of Q1 is 0, the x position of Q2 is 3, 3 squared is 9, and then 4. And I'm going to go ahead and leave our answer inside the radical. It'll make my math a little easier here in a moment. Following the same procedure, the distance between charges 1 and 3 is going to be the square root of 26 meters. Alright, so in this particular problem, we're looking for the force on Q1. Which is why at this point I'm not going to bother with the distance between charges 2 and charges 3. So, we'll start off with what force charge 2 is doing to charge 1. So again, I pull out Coulomb's law. 2 on charge 1 is K times the magnitude of the charges squared over, the magnitude of the charges over the distance squared. So plugging in some numbers here, my proportionality constant, as before, Again, these are in microcoulombs, so I need to go ahead and convert to coulomb. And because I kept my distance inside the radical, when I square that, it's pretty easy to see that square root of 13 squared is 13. My units cancel, leaving me with just newtons. And if I plug this into my calculator, I'll get something that looks like this. Notice that I'm leaving more significant figures than is necessary at this point. I prefer to do my rounding at the very end. So as I go through these examples, you'll often see me leave more significant figures than is necessary. Given the information that I gave you, we really only have one significant figure, so this should be 0.001 newtons. But again, since we have some more math to do, I'm going to wait and save the rounding until the very end. So we know what the magnitude of the force of charge 2 onto charge 1 is. Now we need to look at the magnitude of the force of charge 3 onto charge 1. So this time we're dealing with charge 3 and need to deal with the distance between charge 3 and charge 1. Plugging in my numbers here. You'll note as I'm plugging in my numbers for charge 3, I'm only interested in the magnitude of the charge. I did not include the sign. It's up to you whether or not you want to include the sign at this point. I find it easier and I make fewer mistakes if I focus solely on the magnitude and then find the direction based on the signs of the charges afterwards. So as I go through this problem, I'm only interested in the magnitude of the force, so I'm not dealing with the negative charge of charge 3. If we plug this into our calculators, we'll get 0.003 newtons with a few extra digits there to improve our rounding a little bit later. So now we know what the overall magnitude of these forces are, but because we're dealing with charges on a plane, not on a line, they're not necessarily all pointing in the same direction. So we're going to have to take a look at the vectors of these. So, in order to find the total force on charge 1 in the x direction, we need the sum of all the forces in the x direction. Same goes for the y direction. We need the sum of all forces in the y direction. So, in order to do this, we need to find the angles between these different charges in order to break into our proper vector components. So, taking a look at our diagram here, we've got our positions, we have our distances between them, so we can go ahead and find out the angles between these. So, between charges 1 and charge 2, I will use tangent to find my angle. So if we go back and look at our diagram, we need to go down by 2 and over by 3 in order to get from charge 1 to charge 2. So that's going to give me an angle of 33.7. Similarly, for the angle between charges 1 and charge 3, 1 over 5, I do inverse tangent on that, and I'll find the angle to be 11.3 degrees. So in order to move forward, we need to actually go through and draw a force body diagram, a free body diagram, or a force diagram, depending on what you want to call it. When you're going through and working on these problems, if you're working on multiple charges, trying to find the total force on multiple charges, you need a separate force diagram for each charge. In this particular problem, we're only looking at the total force on charge 1, so we only need to draw the force diagram for charge 1. So let's go ahead. I'll have my y-axis here, my x-axis going across here, and charge 1 is going to be right there in the middle. Now, if we look at the charges on charge 1 and charge 2, the signs of those charges, they're the same. So that tells us that the force that charge 1 is going to feel due to charge 2 is going to be a force away from charge 2. So if charge 2 is over here somewhere, then that means that the force that charge 2 puts on charge 1 is going to be in the opposite direction. And again, we just calculated the angle between those two, so we can put that in here as well. Now, if we look at the force between charge 1 and charge 3, we're looking at opposite signs on those charges. Opposite charges attract, so the force that charge 1 feels due to charge 3 is going to be towards charge 3. So that's going to be something that looks like this. And that's a theta 1, 3, even though it's a little smaller. At this point, I'm not worried about how long my vectors are, if they're pointing in the exact right direction. I know what my angles are, and I know the general direction that my forces are pointing. This is probably the part that's going to trip the most people up, is the vector superposition. So again, when you add up forces due to different sources, that's called a superposition of forces. We'll use that term in other areas as well when we get to fields. The biggest mistake, or the most common mistake people are going to make on this, is mixing up their directions when they're doing their superposition of forces. So this is why I recommend going through and doing the magnitude and then looking at the sign of the charges in order to figure out what direction these forces are going, instead of just putting the sign of the charge into Coulomb's law directly. Alright, so now we know what directions the two forces on Q1 are pointing. We know their magnitudes. So now we can go ahead and break this down into vector components and solve for the magnitude and direction of the net force on Q1. So we'll start with the x direction. So the total force on Q1 in the x direction, again, is the sum of all forces in the x direction. So that's going to be the force of charge 2 onto charge 1 in the x direction, plus the force of charge 3 onto charge 1 in the x direction. So, the force of charge 2 onto charge 1 is pointing in the negative x direction. So we need to put our negative sign in there. And that's going to be the magnitude that we already calculated times cosine of the angle that we've also already calculated. Now, the force due to charge 3 on charge 1 is pointing in the positive direction, so that gives us a positive here. Force of 3 onto 1, also times cosine of the angle between them. If I start to plug in some numbers here, I get negative. I plug in my force due to charge 2 on charge 1 that you can go back and reference from above. Plug in my angle that we've already calculated. And our units here, all of this again is in newtons. So, plugging this into our calculator, the total force on Q1 in the x direction is 0.002 newtons. Since that's positive, that also means that it's in the positive x direction. We'll go through the same procedure for the force on Q1 in the y direction. Alright, so looking at this, both of these forces are in the positive y direction, so we don't need to worry about a negative sign anywhere. They're both going to be positive signs. We do have to break it down into the y, so we are going to have to include some trig here. But the procedure here is very similar to what you did last quarter when you would break your forces down into vector components at that time as well. Plugging in our numbers for the forces and our angles. This is newtons. Everything goes into the calculator. And we get 0.001 newtons for the total force in the y direction. Now we need to take these two vector components and combine them to find the total magnitude and direction of the force on Q1. So just like you've done before, I'll go through as an example. The total force on Q1, it's going to be the force on Q1 in the x direction squared plus the force on Q1 in the y direction squared, everything square root. Plug in our numbers. And since this is the end, I'm finally going to use the correct sig figs, and I get 0.003 newtons. At this point, we don't know what direction though, so we need to go through and look at what angle this is going to be. So we'll go back to our tangent. The tangent of the angle between from the positive x direction up to wherever this force is. It's going to be the ratio of these two, of the x and y vector components of the force. Just like you've done before. Inverse tangent of that fraction gives us the angle. So that means that our total force due to these two charges on Q1 is equal to 0.003 newtons in the direction of 57.3 degrees up from the positive x-axis. And if we go back to our picture, that kind of makes some sense. So we would expect that it would be above, meaning positive y, because both are forces due to charge 1, or excuse me, due to charge 2 and charge 3 were in the positive y direction. The question was whether or not, due to the angles and the magnitudes of the two charges, whether it would end up being in the positive y, or excuse me, positive x or negative x direction. Since the force due to charge 3 was a little bit stronger, it ended up being in the positive x direction. So, there is the end of the 3 charge in a plane example.